In previous videos, we have used energy profiles to depict products, products and reactants and how they are separated by an energy barrier. And in our previous video, we have said that an overall reaction can actually be split on by different steps. R1 and then R1 may become R2 and then R2 may become finally products, whatever that may be. So it may mean that the overall reaction most likely should be split into different elementary steps. It's unlikely that the reactions that we deal with, it's one single step. Some of them may be, but this means that this picture may not represent real reactions because typically the barrier between reactants and products will involve different steps and therefore different barriers, each of them with their own activation energy, if you will. So the graph that you have right here may be more representative of a typical reaction. In this case, A would be your reactants and G will be your products. And notice that we have, if you will, first of all, we'll have how many steps? We'll have the first elementary step going from A to C, the second elementary step going from C to E, and finally the last elementary step going from E to G. I'm not willing to call C and E intermediate because we would need to look at the overall combination of elementary steps, but it's definitely an intermediate step. It's not, we do not know what the composition of C and E may be. Okay, but it's important to realize that each step will have its own activation energy or its own barrier. Okay, so and that will definitely affect the rate of your overall reaction. So let's start answering these questions. It's asking if the reaction is endothermic or exothermic. If we're talking about the overall reaction, notice that G, because the enthalpy of G is larger than the enthalpy of A, what you have is an endothermic reaction. Okay, how many steps are there? We just counted 3, right? So, and there will be as many as transition states. So, as many as transition states. So, B separates A and C, D separates C and E, and F separates E and G. So 3 elementary steps that when combined give the overall reaction. And now let's talk about what the slowest step is. In other words, what step is the step that has the highest barrier in front of it. We will measure the barrier from the reactants in that elementary step all the way to the transition energy. Notice that the first step has the largest barrier, even though the transition state of the second elementary step stands at a higher energy. One could say that the overall barrier is smaller. A side note, this is only true if there is thermal equilibrium, so C achieves complete thermal equilibrium with the environment, if it's a reversible process, whatever. Just so you know, we are taking an approximation when we say that. If you're taking physical chemistry later on and learn about more kinetics, you may learn that that may not always be true. But if we define that the barrier is the energy between the reactants at the transition step, definitely the first step is the lowest step. And because it's the lowest step, you can think of it will be the bottleneck of the overall reaction. In other words, products will be produced as fast as the first step can make its own products. So this means that the overall reaction from going from A to G will have a rate law that will be the same rate law of the first elementary step. Okay, so this is the so-called rate determining step approximation, in which we assume that the bottleneck of the overall reaction, the elementary step that has the highest barrier will be the one determining the rate of the overall reaction. Okay, so let's practice some more. Let's give you an example. This is a common atmospheric reaction. The overall reaction, you have it here. Nitrogen dioxide reacts with carbon monoxide to give nitrogen monoxide and carbon dioxide. And we can measure experimentally that this is the rate law. Notice that the rate law does not match with your overall reaction. So one needs to come up with a mechanism that explains this rate law. Now, this is the mechanism that we suggest, and I will reiterate this, that we usually do not know the mechanism, therefore we suggest the mechanism and we contrast it against the facts that we know about that experiment, such as we know the reactants, and we know the products, and we can investigate the rate law by using the tools that we have been using so far, if it's first order on a specific component or not, and also calculating the kinetic constant, etc. So, does this mechanism match with the observations? First, if we add it up, notice that you'll have 1, 2 NO2s. NO3 disappears, so you have two intermediates in this case. I'm sorry. You only have there you go. So you have two NO2s. I apologize. There is this NO2 also disappears with this one, so let's make sure. NO2 plus carbon monoxide gives NO plus CO2. So yes, this mechanism is a plausible mechanism in the sense that it can reproduce the overall reaction. Now, if we say that the first step is the slowest step, that is, it's the bottleneck, does that match with the observation? Well, because if this is an elementary step, the rate law of the elementary step, we say it would be the observed rate law of the overall reaction. So notice that this is the same. This means that, and this would be a graph representing it, this is our bottleneck of the first step. So the rate at which molecules can pass in the first step will be the rate at which molecules can overall make it to products. In other words, if reactants can make it the first step, they have enough energy to make it all the way to products. That's a little bit the assumption and in this rate determining step approximation. Okay, so yes, this mechanism can reproduce experimental observations such as the overall reaction here, or explaining why the rate law, the observed rate law, the measured rate law is this one. Let's practice one more time. In this case, we have this reaction. Okay, we know typically the initial reactants and the final products, and we can also know the rate law by using the integrated rate laws. You may want to maybe calculate the concentration over time, and you saw that was a straight line. You calculated the slope, gave you the K. So there are ways to know that this is the observed rate law. The question is the mechanism given here compatible with observation 1 and observation 2? First of all, the overall reaction, to be compatible with observation 1, is that the overall reaction needs to be the summation of the different elementary steps. So let's see. And 205 is right here. NO3 disappears. And then I have another N205 here, so two N205s. Now, NO and NO disappears, and I have NO2 and oxygen. Wait, 4NO2. Is that it? Okay. So notice that this, let me make sure I did this correct. There is one single, oh yes, there's two. There is two N205s here. NO3 disappears because it appears both as products and then as reactants. It's an intermediate. Okay. and then NO also disappears because it's first products and then reactants. Okay, so I measured everything. Now there are 1 plus 3, 4 NO2s, and finally there's 1 oxygen. Alright, is this compatible with observation 1? Well, even if you balance this according to that, yes. Yes, I was misled. Yes, it is compatible. This is the exact same reaction of this, so the mechanism is compatible. Now let's look at observation 2. If this is a slow step, that means it's the rate determining step. The rate of this elementary step is K times dinitrogen pentoxide. So this is the rate of the elementary step. If this were the slow one, it would be the observed rate law, which it is. So yes, this mechanism is compatible with those two observations. First I thought that there was going to be 2 oxygens, but I was clearly mistaken. So in this case, this mechanism is a good mechanism. May not be the right one, but at least it can explain both observations. We would need to do more observations to contrast this mechanism further.